All right, let's dive right in. Today, we're going to crack open a robot's brain and see what makes it tick. We're going to follow the life of a single frame of video, from the moment it hits the camera as just a bunch of pixels, all the way until it becomes a command to steer the wheel. And our roadmap for this whole adventure is the brilliant rule-based logic inside the VRR Beta 1.3 system. So this is the big question, isn't it? You have a camera, spitting out a stream of pixels. How on earth does that become an intelligent driving decision? How does a machine know when to hit the gas, when to turn, and how hard? It can feel a bit like magic, but I promise you it's not. It's actually a really beautiful, logical assembly line of decisions, and we're going to walk through it piece by piece. Here's our game plan. We're following what I like to call the journey of a frame. First, we'll look at the spark, the signal that gets everything moving. Then we'll see how the robot builds its worldview, literally finding the lane. After that, it's the moment of decision, where it actually figures out how to steer. We'll even look at a super clever trick for handling sharp curves. And finally, we'll see what it does when it gets lost. Let's get started.
So, our journey starts right here. Before the robot even thinks about steering or accelerating, it has to answer a much more basic question. Has the race even started? This is the very first logical gate it has to pass through.
The solution they came up with is so elegant. A simple state machine. Now, you might think, okay, it just looks for red lights. But that's a trap. Why? Because those starting lights could be on for a whole minute before the race begins. The real insight here is that the important signal isn't just seeing the lights, it's seeing them change state, specifically from on to off.
So here's how that logic works, step by step. First, it's smart. It only scans the top part of the image where it expects to see the lights. Once it sees all three red lights are on, it flips an internal switch, a little flag that says, okay, I'm ready. But, and this is the most important part, it doesn't move yet. The actual go command only fires the instant those lights turn off. That two-step process makes the whole system bulletproof against false starts. And we're off. The race has started. Now the robot's main job kicks in full-time, perception. Frame after frame, it has to answer the question, where is the road? This is all about taking a messy, noisy image and turning it into a clean, mathematical model that it can actually drive on.
Okay, so the first step in perception is to ignore all the junk data. This system does that in two really clever ways. First, instead of using standard RGB, it converts the image to the HSV color space. This is huge because it separates a color's brightness from its actual hue. So a white line in a deep shadow looks a lot more like a white line in bright sunlight. Then it applies a region of interest, an ROI. It basically just tells the computer, hey, see the sky and the hood of the car? Just ignore them. This saved a ton of processing power.
And this right here is the actual recipe for white in the code. It's so cool. It tells the system, I don't care about the hue, because white has no color. Just find me pixels that have super low saturation, meaning they're not colorful, and super high value, meaning they're really bright. These simple rules just slice through all the visual noise and give you a perfect black and white image of just the lane lines. So now that we have our clean image, how do we actually trace the lines? With this really cool technique called the sliding window algorithm. First, it just looks at the bottom of the image and finds the two biggest clumps of white pixels. That's the start of the left and right lanes. From there, it launches a stack of little search boxes or windows that crawl up the image. Each window finds the pixels inside it, recenters itself on them, and then tells the next window above where to position itself. It's an incredibly efficient way to follow the curve of the road.
And after all that searching, after finding all those hundreds of little white dots, what does it all boil down to? This one beautiful, simple equation. A quadratic polynomial is the robot's entire understanding of the road. It is the lane line. It's so powerful because you can describe almost any curve on a road with this kind of equation. It's a perfect predictive model of the path ahead. It's just incredible. Okay, so the robot has its mathematical model of the lane. It knows where to go. Now what? Well, now it has to actually act on that information. We're moving from the world of perception, of seeing, into the world of control, of doing.
The control system really has to solve two problems at the same time. The first is heading error, basically asking, which way am I pointing? The second is lateral offset, which asks, where am I in the lane? Think about it. You could be perfectly in the middle of the lane, but pointed straight at the wall. Or you could be pointed perfectly down the track, but you're about to scrape the side. A good driver, or a good algorithm, has to correct for both at once. And this is how it's done. This simple line of code is a classic proportional controller. It's basically just a recipe. It says,
Take a portion of your heading error and add it to a portion of your position error. And that's it. That's your new steering command. It just elegantly blends the solution to both problems into a single, clean action. So what are those K values? Well, you can think of them as the robot's driving personality, and the engineers have tuned them very carefully. The gain for heading, K theta, is set pretty high at 0.90. That means the robot is aggressive about pointing itself in the right direction. But the gain for position, K lateral, is a bit lower at 0.60. It's more relaxed about being in the exact dead center of the lane. Finding this perfect balance is the real art of control engineering, making a system that's responsive but not unstable and twitchy. Now, that simple formula works great on straightaways and gentle curves. But what happens when you hit a really sharp turn? Well, that's where some clever, human-inspired engineering has to step in. Okay, this might be my favorite part of the whole system. It's just so smart. The engineers built in a technique they call tap-tap throttle. When the robot realizes it's in a sharp turn, basically when its heading error is more than 25 degrees, it stops applying continuous throttle. Instead, it starts pulsing the power, just like a human race car driver would do to keep traction. It's such a simple rule, but it solves a really complex vehicle dynamics problem. And you can see the rhythm right here. It's perfect. Power on for 3 frames, coast for 3 frames. On, off, on, off. This isn't random. It's a very deliberate cycle. That off phase gives the car a split second to settle, breaking its forward momentum and letting the front wheels really bite and pull the robot around the corner. It's just pure, elegant control. So we've seen how the system works when everything is going right. But in the real world, things go wrong. A truly robust system isn't just defined by what it does when it can see the road, but what it does when it can't. This system has a 2-stage plan for when it gets lost. For the first 2 seconds after losing the lane lines, it goes into hold mode. It assumes the lane is probably still straight ahead, so it just keeps going with its last known steering angle while gracefully slowing down. But if 2 seconds go by and it still can't find the lane, it escalates to search mode. It stops moving forward and just starts to slowly pivot in place, actively scanning to find the lines again. And that graceful slowdown in hold mode, it all comes down to this one number, 0.9. It's a decay factor. Every single frame, the system just multiplies the last speed and steering values by 0.9. This doesn't cause a sudden stop. It creates a smooth, exponential slowdown. It's a beautiful, simple piece of math that lets the system feel gracefully instead of just slamming on the brakes. So there you have it. From pixels to pavement, a complete, elegant, rule-based system. Every decision it makes is traceable. Every parameter is tunable. It's a real testament to classic, solid engineering. But of course, this is just one way to solve the problem, which really leaves us with one final question to think about. If you were starting from a blank page, how would you teach a robot to drive?